In the last class, we had seen impedance-based identification. If you recall, so if we are just considering the 2D equation, experimentally we are obtaining the real and imaginary components of the admittance. Then solving this equation, we can obtain the mechanical impedance of the structure Z. So Z will have two components, X and Y, the real part and the imaginary part. So we have to identify some system which fits into the structure, the variation of the mechanical impedance. So we'll see with example. So I have some example to run with the MATLAB code. So if you just recall, I had shown one example. So I'm just taking you to the slide. So if you recall, I had covered the testing of steel joints for suitability of the EMI technique for fatigue kind of damage. So here we had shown that we used the root mean square deviation, so that did not give a consistent result. So we had switched to the impedance approach. So impedance based approach, it showed that within this range 110 onwards, the behavior of the structure, it was like a parallel spring damper combination. So for this combination, the C component is nothing but this is the X itself. So if we just take average value of X, that is the C. And how do we get K? What we have to do is we obtain the Y and we multiply it by omega, that gives us K. So that is basically slope of the Y versus the omega inverse. So that is this slope, and we could see that as the strength of the specimen went down, the slope and hence the resulting stiffness also went down. So today we have example. So I have some data. So I'm just unsharing this PPT, and in place of this I would be sharing the MATLAB screen. Okay, so here I have created one folder, impedance based EMI technique. So this is the version of MATLAB based on the cloud. So here basically I have some data. So I have one set of data before damage and I have another set of data after damage. So I'm first opening the MATLAB program which does this computation. So it basically is just algebra, nothing else, just a complex algebra. So if you have the values of G and B measured from experiment. So for example, here we have the file. So we are inputting this file, text file. So this consists of the frequency, the real part and the imaginary part. It's just like signature which you have acquired from your test specimen in experiment number 5. So similar kind of text file is there. So it reads this file, and then here are the important parameters. Here half length is 5 mm. So in meters is 0.005, thickness is 0.3 mm, density D31, coefficient, the Poisson's coefficient, Young's modulus, the electric permittivity, the mechanical loss factor, the electric or the dielectric loss factor, all are input here. And here is the program. So here in the data, the frequency is given in kilohertz. So first of all, it multiplies with 1000 to get it in hertz. And once this is done, then it does the calculations. So here is the calculation of the wave number. So wave number K is a complex number. So the program has to calculate tan KL by KL. So KL itself is a complex number. So it uses exponential functions for that purpose, so that the complex number they are accounted for when computing tan KL by KL. After that is the calculation of the mechanical impedance of the PZT patch, and after that is the calculation of the structural impedance Z. So Z has two parts, X and Y. So it is how this goes on. So here, after calculation of the X and Y, so what the program does, I am just highlighting this portion. So it is basically now calculating the equivalent stiffness from the Y function. Just now I had shown you, if you plot Y versus the inverse of the frequency, that gives us the slope, gives us the equivalent stiffness. So this is what is there, and then it calculates the average value. First it calculates at all points, then it calculates the average value here. So if we run the program, then we get the answer. But before we do the calculations, first of all we have to identify what system is it. Alright, so what I am doing is that I am just running this program, and I am feeding here the data P0. So if you see here, this is the file name p0a.txt. So I am just running it. So now two figures are being plotted. I hope you are able to see the figures. Are you able to see the figures? I hope the figures are visible to you.
Yes, sir. Yes, sir.
Yes.
Okay, figure 2, and first is the figure 1. So figure 1, this is the real part of the mechanical impedance, now Z. So Z is positive, the real part is positive. And if we see the imaginary part is like this. It is negative and the value is going down. So what kind of system is this? And to help you, what I'll do, I'll just project you the standard plots. So I'm just unsharing this for a couple of seconds and then sharing the PPT. Can you identify the system? In fact, the system is similar to this parallel spring damper.
The first one.
First one, right? Why? Because here this is constant, the x part or the real part is constant and the imaginary part is negative, and the asymptotically the negative part, it reaches 0. From some constant negative value it reaches 0, right? So now I take you back to the MATLAB screen. So now are you able to see that for the damage case, what is the scenario? Again, the real part is positive, of course there is some variation, and the imaginary part, it is again negative. And the program has calculated now the stiffness, changed the modified stiffness as 4.57 into 10 power 7. Can you read this figure? 4.5696 into 10 power 7. I hope, can you read this figure? 4.56 into 10 power 7. So this is the reduced stiffness. So this is the impedance-based identification. So here we are not relying on the visual change, but we are relying more on something very specific parameter, the stiffness. Also, this is better than the root mean square deviation, which is non-parametric in nature. So any doubt till now? Let me show you another example after that. If you have any doubt, then you can ask. So this program and the data I'll share. So let me now.
It is reduced after due to damage.
Yes.
5.22 to 4.
Exactly. So this data is for the same aluminum block. In my last presentation, I had shown you the aluminum block where holes were drilled. So this is for that block itself. So with damage, this has reduced. Let me show you another example. So what I do is that I have another example, and let me close this. Basically, it's the same program. The program is same, which basically identifies the x and y, means calculates x and y and then plots them. So this is also I'm running. So here I have given the input file, another file name. So now can you see the variation? This is the real part x. This is the real part x versus frequency. And then we have the imaginary part y versus frequency. Now could you see any change, any difference?
Yes, sir.
Now here the imaginary part, the variation is totally different.
Totally different, yes.
So what you can do is just on your paper you plot the variation, that the imaginary part it's linear, more or less linear, changing from positive to negative, right? Changing from positive to negative. And the real part is like you can say it's fluctuating, but if you see here the fluctuations, they are very small. The variation is only from 3.5 to 5. So more or less this is a constant. More or less this is constant. So the constant value or the average values will be something around 4.5. Okay. So now I show you the systems and you identify which system is this one. Okay, I'm unsharing this and sharing again the PPT.
Yes, sir.
Now for the second case, could you identify the particular system? Which system is this one?
Sir, it is not matching with the system because this is the linear variation which you have shown in the MATLAB. But last one, this is not serial number 7. It is not a linear. It is some parabolic. Yes, some non-linear variation.
But then if I say which is closest? Which is closest?
If closest, then number 7.
Number 7. See, if you limit number 7 to a small frequency range, then it will tend to be a linear. Even if it has certain curvature, but over a small frequency range, it will be more or less linear. You can always approximate it like a linear one, near the region where it's crossing the x-axis. Okay, so the closest is number 7, which is series KMC system.